For decades, astronomers believed they understood the basic shape of our galaxy. A graceful spiral, rotating calmly in space. A thin, luminous disk of stars. And at its center, a dense, roughly spherical core, wrapped in gas, dust, and an invisible halo of dark matter. It was a simple picture. Too simple. Because when scientists finally looked at the Milky Way's heart with the right kind of eyes, the galaxy began to reveal something deeply unsettling. Deep in the galactic core, something is glowing. Not in visible light. Not in radio waves. But in high-energy gamma rays, the most energetic form of light known to physics. And that glow shouldn't be there. In 2009, astronomers began observing the sky in gamma rays with unprecedented sensitivity. For the first time, they could see the universe not as we evolved to see it, but as it truly behaves at its most extreme. Almost immediately, something strange appeared. At the very center of the Milky Way, gamma rays were pouring out far more intensely than any existing model predicted. Not from a single compact source. Not from the supermassive black hole at the core. Not from known supernova remnants. Instead, the emission formed a broad, diffuse glow stretching across thousands of light-years. It was too bright to ignore. Too structured to dismiss as noise. And too persistent to be a statistical fluke. This anomaly became known as the Galactic Center Excess, a neutral name for a mystery that quietly challenged everything astronomers thought they knew about the galaxy they live in. At first, the reaction was cautious. Gamma rays are produced by extreme objects. Neutron stars. Pulsars. Black holes. Exploding stars. The universe has no shortage of violent processes, and astronomers assumed this glow would eventually fit into one of those categories. But years passed. And the excess refused to go away. The data improved. The maps became sharper. The signal stayed. Two explanations began to dominate the debate. The first was grounded in known physics. Millisecond pulsars, the collapsed cores of massive stars, crushed into spheres no larger than a city, spinning hundreds of times per second. These objects are among the most precise clocks in the universe, and they are known to emit gamma rays as narrow beams that sweep through space. Individually, a single millisecond pulsar is faint. But the galactic center is crowded beyond imagination. If thousands, or even tens of thousands, of these objects were hidden there, their combined emission could naturally reproduce the observed glow. It was an elegant explanation. But there was a catch. Despite years of observation, astronomers could not directly detect enough pulsars in the galactic center to fully account for the signal. The region is choked with dust, gas, and turbulent magnetic fields. Radio waves scatter. Optical light is absorbed. Even X-rays struggle to escape. The pulsars, if they exist in such numbers, are exceptionally well hidden. The second explanation was far more unsettling. Dark matter. For decades, physicists have known that visible matter accounts for only a small fraction of the universe's total mass. Galaxies rotate too fast. Clusters hold together too strongly. Gravitational lensing bends light where no ordinary matter exists. Something else is there. Something invisible. If dark matter particles can collide and annihilate each other, theoretical models predict they should release gamma rays with specific energies. The galactic center, being dense in both stars and gravitational potential, would be the perfect place for such interactions to occur. Detecting this signal would not just explain the gamma ray glow. It would provide the first indirect evidence of dark matter itself, a discovery on the level of finding atoms or uncovering DNA. For years, astronomers believed geometry held the key to choosing between these two explanations. The shape of the glow mattered. When researchers mapped the excess in detail, they found it wasn't perfectly round. Instead, it appeared elongated and box-like, almost resembling a peanut when viewed edge-on. That shape closely matched the structure of the Milky Way's stellar bulge, the dense, bar-shaped distribution of stars at the galaxy's center. This seemed decisive. Stars form bars. Stars host pulsars. Dark matter, by contrast, was assumed to form smooth, spherical halos. If the glow followed the stars were probably responsible. For more than a decade, this reasoning pushed the scientific consensus toward pulsars and away from dark matter. But there was a problem hiding beneath that logic. It relied on an assumption that had never been directly tested. The assumption that dark matter halos are always spherical. Recently, a team of astronomers decided to question that idea. Instead of relying on simplified models, they turned to high-resolution cosmological simulations, digital reconstructions of galaxies evolving over billions of years. These simulations don't treat galaxies as neat, isolated systems. They allow them to collide, merge, stretch, and distort under gravity, just as real galaxies do. And when the Milky Way was allowed to evolve naturally in these simulations, something remarkable happened. The dark matter halo didn't stay round. Near the galactic center, gravitational interactions with the stellar bar distorted the halo itself. Over time, the invisible matter was stretched and reshaped, forming a triaxial, box-like structure that closely mirrored the visible stars. The dark matter adapted to the galaxy, not the other way around. When researchers simulated gamma-ray emission from this deformed dark matter halo, the result was startling. The predicted glow matched the observed galactic center excess just as well as pulsar-based models did. The very feature that once ruled out dark matter, its shape, was no longer exclusive. The strongest argument against dark matter simply collapsed. This did not prove that dark matter was responsible. But it showed that the case against it had been built on an oversimplified picture of how galaxies evolve. Suddenly, the debate changed. The question was no longer, what shape is the glow? It became, what physical process is actually producing it? Millisecond pulsars remain a strong candidate. They are real, they emit gamma rays, and the galactic center is exactly where a hidden population could exist. At the same time, dark matter is once again a serious contender. If annihilation is occurring there, it would connect cosmic structure formation to fundamental particle physics in a way never before observed. Either outcome would be transformative. The implications reach far beyond this single glow. If dark matter halos can be distorted by galactic evolution, it could affect how astronomers interpret rotation curves, stellar orbits, and gravitational lensing not just in the Milky Way, but in galaxies across the universe. It suggests that dark matter is not merely a passive background, but an active participant in shaping galaxies. A decisive test is now approaching. A new generation of gamma-ray observatories will soon observe the galactic center with dramatically improved resolution. These instruments will be able to distinguish between smooth emission and thousands of faint point sources. If the glow fragments into discrete dots, pulsars will almost certainly be confirmed as the cause. If it remains smooth and continuous, dark matter will once again move to the forefront. For the first time, the universe may be forced to answer directly. The center of the Milky Way is no longer just a crowded region of stars. It is a laboratory for some of the deepest questions in science. A place where gravity, matter, and time collide. A place where visible and invisible structures overlap. The gamma-ray glow is still there. The mystery remains unresolved. But one thing is now clear. The Milky Way's core is not as simple as we once believed. And dark matter, long pushed aside by geometry, is back in the game. The heart of our galaxy may be stranger, more complex, and more revealing than we ever imagined.